Dear students, in this video we are going to see tree and spanning tree. What is trees? A tree is defined to be a connected acyclic graph. The following properties are satisfied by a tree. There exists a path between any two vertices of the tree. Second point, this is first point. Second point, no cycles must be present in the tree, that is trees are acyclic. First one is tree, these two not a tree. Why? We will see. See the first point, there exists a path between any two vertices of the tree. Yes, here this is a vertex, this is a vertex, this is a vertex, this one, this one, this one. You see, if you take any two vertices, for example, you take this and this, yes, there is a path from this vertex to this vertex and from this vertex to this vertex to reach. So there exists a path between any two vertices of the tree. Yes, not only for these two vertices. If you take any two vertices, yes, you can go. You have a path. Okay. First condition is true. See the second condition. No cycles must be present. Which means no cycles must be present in the tree. Yes. Here you see no cycles. Suppose I have one edge from here to here, then that will form a circuit or cycle like this. If suppose here there is an edge, but no edge here, so no cycle. Similarly, no edge here, no edge here, so here no cycle. Here no cycle in this tree. That is, trees are acyclic. Tree means should not be containing any circuit, should not be containing any cycle. That is tree. Okay, this is tree. Now you see this one is not a tree. Why? You see there exists a path between any two vertices of the tree. Yes, there is a path between any two vertices. That is, first point is right. See the second point. No cycles must be present. But here there is a cycle. You see here from here to here, edge here to here, here. This is a cycle. Cycle is not allowed in any tree. So this is not a tree. So this is not a tree. That is given here. Now see this graph. You see this vertex 1, 2, 3, 4, 5. You can reach from this vertex to this vertex by this path, but you cannot reach from this vertex to this vertex or this vertex to this vertex. So first point is here false. There exists a path between any two vertices of the tree. This is actually disconnected. This is not connected. These three vertices and these two vertices are separated. It's not connected. So this is not a tree because first condition is false here. Now we'll see what is a spanning tree. Now a spanning tree is a subset of edges from a connected graph that, again, two conditions, touches all vertices in the graph, spans the graph, simply we can say, touches all vertices in the graph. Second, forms a tree, is connected and contains no cycles. What is a spanning tree? Spanning tree means touches all vertices. All vertex you have to cover, that tree has to cover all the vertices. At the same time, should not contain any cycle. At the same time, it was to form a tree. That is called a spanning tree. Now you see the example, you can understand. A subset of edges from a connected graph. No need to cover all the edges, but all the vertices should be covered. That is very, very important. See, touches all the vertices. All the vertex you have to cover in the graph. At the same time, should not contain any cycle or circuit. See, no cycle or circuit. but it has to form a tree. It has to form a tree, which means it should be connected. Okay, now you see the example. This is the given weighted graph. Okay, now here 3 spanning trees are there. Yes, see here 1, 2, 3, 4 vertices in the given weighted graph. You know why we are telling weighted graph? Because this edge is having some weight. It may be the kilometer or some unit. So this is called the weighted graph. Now here we have covered 4 vertices and no cycle. This is connected and it forms a tree. Therefore this is a spanning tree, which means you should touch all the vertices, means all the vertices should be covered by the edge and it should be connected and it should not be having any cycle. That's why this is a spanning tree. This also a spanning tree. This also a spanning tree. Okay, now you see the weights of the edges. Now you see 7, 2, 4. So 7 plus 2, 9 plus 4, 13. 7 plus 1 plus 9, 10, 17. Total weight, I am writing total weight. Now 9 plus 7, 16 plus 4, 20. This spanning tree having weight 13. This spanning tree having weight 17. This spanning tree having weight 20. Now all 3 are spanning trees. But what is the next definition? That is minimum spanning tree, which means spanning tree with the least total edge cost, with total weight of the edges. Okay, now you see here 13, 17, 20. But yeah, this is the only minimum spanning tree. No, actually this is not even minimum spanning tree. Yes, we can find some other. You see here A to D and then D to C and then B means C to B. You see A, D, C, B. This is a spanning tree and minimum weight because A to D 2, D to C 4, C to B 1. So 2 plus 4 6, 6 plus 1 7. The total weight is 7 for this spanning tree. So this is minimum spanning tree. Now we can see few examples. Now you see here examples. Now this is the undirected graph having 4 vertices and 1, 2, 3, 4, 5 edges. Now spanning tree. This is a spanning tree. See here you see the dark edges. You see, start from here, this one and this one, this edge, second edge and the third edge. Yes, this is a spanning tree with weight. You see here 4 plus 5 plus 2, 4 plus 5 plus 2. So total weight is 11. This is a spanning tree. Okay. Now this also spanning tree. See from here to this vertex and then this and then this. Now what is the total weight? 4 plus 1 plus 2, that is 7. Here the total weight is 7. Here the total weight is 11. This is a spanning tree. This also is spanning tree, but the weight is minimum here. The weight is minimum here. That's why here we are telling minimum spanning tree. This is the minimum spanning tree. Now you see another example. This is a given graph. Okay. Now you see the spanning tree. Start from this vertex, from here to here, here to here, here to here, here to here. So 3, 2, 3, 5. The total weight is 13. Now you see here, this is also a tree. This is also a spanning tree. This is also a spanning tree. Why? No cycle and all the vertex covered and connected. 3 conditions. No vertex, all the vertices covered and then connected. So this is a spanning tree, this is also a spanning tree, but you see the weight. The total cost is 13 here, the total cost is 7 here. That's why I am telling this is minimum spanning tree. Put extra one word. So this is spanning tree, this is minimum spanning tree because the total cost is 7. Now you will see here one algorithm. What is this? This is called Prime's algorithm to find minimum weighted spanning tree for the given graph. Now we have 5 steps for this. That is, step 1 is select the edge with the smallest weight from the given graph. Second step, find all the edges that connect the tree to new vertices. Third point, find the least weight edge among those edges and include it in the existing tree. Step 4, if including that edge creates a cycle, then reject that edge and look for the next least weight edge. Step 5, keep repeating steps 2, 3, 4 until all the vertices are included, because what is the condition to find the minimum spanning tree? All the vertices should be covered and there should not be any cycle and must be connected. At the same time the weight should be minimum, then only we can say that is minimum spanning tree. So to find the minimum spanning tree from the given graph, we have to use this algorithm, Prime's algorithm, by applying these 5 steps. Okay, we will see how to apply this Prime's algorithm for the given graph to find the minimum spanning tree in the next video.